finish our classification of discontinuities, we move on to those of infinite type, and this will be more clear what is meant from the visual examples from the following graphs. And if you remember, removable discontinuities were those where we actually had a limit as f approached a number, but the value of the function was not equal to that limit. And the jump discontinuity, when you would see a jump in the graph where both right and left some limits existed. In turn, infinite discontinuities happen when one or both of the one-sided limits are infinite, even if f of x is not defined at x equals c. So that's completely irrelevant for the classification of this type of discontinuity. So it may happen, like in the first drawing here, that both sides of C, you don't have a limit, so f is not approaching anything, but rather it's increasing without bound. The left of C and the right of C, so that the limit is formally plus infinity on both sides. Here, so here, for instance, the limit of f of x as x approaches C from the right is plus infinity. And it's the same thing for the limit from the left. Here in the second example, you have also an infinite type discontinuity. Here the limits from the right and from the left are not the same. The limit from the right is minus infinity, while the limit from the left is plus infinity. It can also happen that you have a right-hand limit, like in this case, the limit of f of x as x approaches 0 from the right is equal to a value L. However, the limit of f of x as x approaches 0 from the left is minus infinity. And also here we see that the limit of f of x, so this number here is c, the limit of f of x as x approaches c from the right exists, whereas the limit of f of x as x approaches c from the left is equal to plus infinity. So you can think of all the combinations, and they're all sufficient to classify this kind of discontinuity as an infinite discontinuity. And that's because, I mean, if it happens that on either side of the point C, f is either increasing without bound or going to minus infinity, then that's an infinite discontinuity. And that's actually with disregarding what happens at x equals c itself. F may be defined at the point, like in these two cases, and it may be even right continuous, as in these two cases, but the function exhibits an infinite type discontinuity at the point, regardless. Okay, so that's more or less finishes the classification of discontinuity. So we have removable, we have jump discontinuities, and infinite type discontinuities. Now, of course, there are several other ways in which you can observe which discontinuities can happen. One is something we had already seen with the case of the function sine of 1 over x at the origin. And this is the kind that, so I said, the same, for example, in the case of the function sine of 1 over x. Oscillates between -1 and +1, infinitely often near 0. So this is a case where there is no jump. The function is bounded. However, the oscillatory behavior of the function prevents it from being continuous, or prevents that discontinuity to be repaired, because there's no way of assigning a value, for instance, for the function sine of 1 over x at the origin that would make it continuous, because there's no limit. There's no limit of sine of 1 over x at the origin from either side of x equals 0. So having seen all that, having classified the discontinuities of a function, we move on to the basic laws of continuity. If you remember from last week, all of these laws will correspond to, we have an analog in one of the limit laws. So for instance, we know now that if f and g are continuous at a point c, then the sum and the difference of the two functions is also going to be continuous at the point c. And if you multiply a continuous function at a point c by some constant, then that is also continuous at the point c. The same holds for the product and for the quotient, as long as the denominator doesn't vanish. So this is very important, and you need to check. And this was also present when we were considering just the limit, the law of limit law corresponding to the quotient. We need to assume the denominator is defined at the point, so does not take on the value 0. Okay, so if this is the case, then 1 through 4 are continuous functions. Just going to give a quick example. Say we give a quick example of I. Let's consider f of x equals x and g of x equals x squared minus 3. Then f of x minus g of x, which is equal to x minus x squared minus 3, which is x minus x squared plus 3, is continuous at every point in the domain of f of g, which happens to be the real. So the real line, the real numbers. Okay, for the last property, so for the quotient, we may consider function f of x, which is the tangent of x. If you remember, the tangent of x can be written as a quotient, so you can write f of x as some g of x over h of x, where g is the sine of x and h of x is the cosine of x. So this quotient will be continuous at every point. The sine and cosine are continuous everywhere, you will see, but at every point except at the points where cosine becomes 0. So is continuous at x equals pi over 4 because sine and cosine are continuous there, and we need to check one more thing, and that is that cosine of pi over 4 is not equal to 0. However, maybe I won't have enough space over here, but so however, tangent of x is not continuous at x equals pi over 2. Why? Cosine and sine are continuous, so sine and cosine are continuous everywhere, in particular at that point. But, so there's a big but, cosine of pi over 2 is 0. So if we go back to the quotient law, we see here that we need to have the g of c at the point here is different from 0. Okay, so we also have the continuity of polynomial and rational functions. So if p and q are polynomials, then p and q are continuous on the real line, and the quotient is also on its domain, and that means that all values x is equals c such that q of c is different from 0. So example, let p of x be equal to x cubed minus 5x minus 2, and q of x be equal to x squared minus 2x plus 1. Then the quotient is continuous at every point in its domain. So that means at every point other than the roots of q of x. Q of x is equal to x squared minus 2x plus 1, which is equal to x minus 1 squared. And this vanishes only at x equals 1. So this function is continuous everywhere. In the whole real line, except of 1. Okay, we have also that most of the functions that you've seen or heard of in the past or in previous courses are continuous. So y equals x to the y, where n is continuous in its domain for n a natural number. Sine and cosine, which is a fact that we used in one of the previous examples, are continuous in the real line. Exponential functions are also continuous on the real line for b to the x, where b is greater than 0 and b is not equal to 1. And the log base b of x is continuous for x greater than 0, for b greater than 0 and b not equal to 1. Okay, so in particular, example, so e to the x natural log of x, and using the quotient law we can get the 10x and all other secant, all other trigonometric functions are continuous in their respective domain. So as a rule of thumb, whenever you see a function made up of polynomials or exponential functions, roots, or some combination of those, it will be continuous wherever the expression makes sense. So for instance, the square root of x is not continuous at x, say, equal to minus 1. The function is not even defined there. Okay, but if it makes sense, then to plug in that number, then the function is continuous at that point. So for secant, secant of x is continuous again. Going back to the example that we discussed earlier, secant is continuous at x equal pi over 4, pi over 3, but not at x because secant secant of x is not defined there. Okay, so if you look at, if you counter functions, again, there are products or compositions or quotients, such as the trigonometric functions, roots and exponential functions, and all that, and they are all continuous wherever whenever you are in their domain, the respective domains, and they're not continuous when they're not defined, when that's there.